So here's an example using the inclined plane. We got a crate, fun thing. It's got all sorts of goodies in it, probably wonderful things, as we know. And it's placed on an inclined plane at an angle of 30 degrees. And we got a mu static and a mu kinetic. We have the values here, 0.4 and 0.2. No units, remember, because that's how mu and static and kinetic are. They're just ratios of two forces, so no units. We want to determine the force of static friction, the force of kinetic friction, and the acceleration if there is any. Of course, if there is any, it's possible that the mu static is high enough to just hold the crate in place on that inclined plane. That's certainly possible if the mu is high enough, and that's what we're going to try to figure out. All right, so I've written these expressions down. Mu static times force normal is the force of friction. And remember from force normal before is mg cosine theta. Mu kinetic times force normal is mu kinetic mg cosine theta. For this particular case, I wrote down the result from last time that we can use, but I don't want to make this formulaic because there could be other forces involved sometimes that maybe want to push the object up the hill, etc. So this is only good for this one specific case. So I want to be very careful about using it. I know I can in this case, but it's not always true. Well, let's go back to our diagram from before, just so that we know where things come from. Force of friction is mu times force normal, and force normal is pushing up perpendicular to this surface, and that surface has a force pushing down on it. It's mg cosine theta. It's a function of this angle over here. All right, and we have certain values associated with it. I think theta was 30 degrees, and we have a mass of 50 kilograms. The acceleration, if there is an acceleration, is related to this over here. This would be positive if this expression says if mu is low enough, this will be positive. If it's too high, it'll be negative. And what that means is that it would just stay stuck on the surface. So that's what we're going to analyze numerically to see what's going on. All right, so going back to our problem, let's try a few things out by plugging in some numbers. Now that we've got some expressions over here. We also know that the force downwards, so we have the downwards force along the inclined plane related to the sine of the angle. So that's mg sine of theta. And what we can call this is the force along the plane. Like that. Not an airplane, but the inclined plane as such. All right. So what do we have over here? Let's try to figure out, first of all, if this number is positive or negative. That'll tell us if it's accelerating. And if it is, what that also means is that mg sine of theta is going to be greater than force of friction static here, like that. All right, so let's try this out. I've got g, 9.8 meters per second squared times the sine of theta minus mu cosine theta. So I got my parentheses going. And sine of 30 degrees, all right, minus mu, which is 0.4 for the static case. We want to test that first. 0.4 times the cosine of 30 degrees, like that. All right. And what I get is 1.5 positive. It's a good sign. So it is accelerating at some fraction. It's lower than 9.8. That's a good gut check. If we got a value higher than 9.8, be pretty concerned about that. So what that tells me is that this value here, mg sine of theta, is going to be greater than mu static times force normal. It's going to be greater than the static friction. So it overcomes that and starts sliding based on this over here. All right. Now, it's actually not sliding at 1.5 meters per second squared. It's going to be faster than that. Here's the reason why. I checked this with the value of mu static just to see if it was going to be some kind of acceleration. But of course, we know when it starts moving, that's when kinetic friction takes over. So this mu actually would be the 0.2 from before. All right. So just as a reminder from the other page here, we had mu static was equal to 0.4 and mu kinetic was equal to 0.2. All right. So I'm going to do part 3 first, since I already had that set up. So it's not some fraction of 9.8, 9.8 times sine of 30 degrees minus mu, which now is the kinetic one, times so 0.2 times the cosine of 30, like so, and we got 3.2. All right, so the actual acceleration, now that we know it's going to actually move, is 3.2 meters per second squared. Great. So let's do this comparison now. Let's try to find that net force, okay? We'll double check our answer as we go along to make sure this is right. This is the force down the plane, mg sine of theta. So remember that the m is 50, okay, times 9.8 times the sine of theta, okay? And that is 30 degrees, all right? So I get 245 newtons down the slope, all right? So this here is 245 newtons, and it better be greater than this guy over here. I think it is. This result that we got before certainly suggests that when we checked before. But let's do it from this perspective. All right, so we got mu static, that's 0.4 times mass of 50 times the acceleration of gravity times the cosine of 30 degrees. All right, I get 170. So yeah, definitely way greater, 170 newtons. But that's not the net force. That's just telling us that it's exceeding the maximum hold of 170 newtons. So let's figure out how much static friction there is, rather kinetic friction now. Here we go, mu k is 0.2 times 50 of mass times 9.8 g times the cosine of 30, like that. And I get about 85 newtons, okay? So considerably less. All right, what's the net force? Well, I've got 245 down the slope. Resisting is friction, kinetic friction, which is 85 newtons. So the difference between the two, I go 245 plus negative or minus 85. The net force is 160, all right? So F net in the x direction is 160 newtons, okay? And that equals MA. Well, A, in this case, would equal 160 divided by M, which is 50, like that, all right? I think that's what we got. 245 minus 85, yep, 160 divided by 50, and I get 3.2. Surprise, surprise. Nice, physics works. All right, so we did it the formal way here by finding the forces. It double checks our original result over here where we got 3.2 meters per second squared using the result from the last lesson, this expression for acceleration. And that's great. The fact that we were able to get two different angles is very powerful. And this is a very formal method here of doing it, finding the forces and then setting them equal to MA. We got it. All right, so that's the basic sample with numbers. And moving on, this is the final topic in forces and friction for the time being. So hope if you got this, then you're on top of our game. Nicely done. Morad, out.